Welcome everyone to another deep dive. Today we're jumping into, well, frankly, one of the most fascinating debates in modern physics. It's a conversation that really makes you question, the fundamental nature of reality itself.
It really does. And we're digging into some pretty radical ideas from Jacob Barandes, a physicist over at Harvard. He was on the Theories of Everything podcast and laid out some thoughts that could genuinely shake things up. We've tried to boil it down for you.
Yeah, imagine this. All that quantum weirdness you hear about entanglement, the measurement issue.
Yeah.
What if it wasn't inherently weird at all? What if it just dissolved? Because we questioned one underlying assumption.
Exactly. That's the core of Barandes's claim. He fingers this concept called Markovianity as the hidden piece of the puzzle we've maybe overlooked.
So our goal here, for you listening, is to shortcut you to getting your head around this. We want to give you those, surprising facts, those aha moments where it all suddenly clicks.
Mm-hmm. Because if the Barandes is onto something, this whole quantum mystery might be clearing up sooner than we think. Quantum clarity, maybe?
I like that, quantum clarity. Okay, let's get into it. What's the main thrust of his argument?
Right. So Barandes starts by pointing out that quantum mechanics and classical probability theory, they're actually structurally very, very similar, way closer than most people think.
Okay, so what separates them then, in his view?
It's this assumption, Markovianity. He argues that's the dividing line we've drawn, maybe without even realizing it fully.
And Markovianity itself. Can you break that down? What does that actually mean in, simple terms?
Sure. So think of a Markov process like predicting the weather tomorrow based only on today's weather. You completely ignore yesterday, last week, everything else. The future depends only on the immediate present state. No memory.
Okay, no memory. Got it.
But quantum systems, Barandes suggests, aren't like that. They're more like trying to understand the next sentence in a novel. You can't just read that one sentence in isolation, right?
Right, you need the paragraph.
Yeah.
Maybe the whole chapter to really get the meaning.
Exactly. Context matters hugely. And that's his point about quantum mechanics. It seems to have this memory, this dependence on context that simple Markovian processes lack.
So the big implication then is, if we just drop the Markovian assumption,
then quantum mechanics might just look like a perfectly natural extension of classical ideas, a non-Markovian extension, and suddenly all that spooky metaphysical weirdness might just evaporate. It's not needed to explain things.
wow, okay, that's a big shift. If that's the case, how does it change how we look at, say, the quantum measurement problem, or even local realism?
Yeah.
Especially after the 2022 Nobel Prize.
Ah, yes, the Nobel Prize. It celebrated those experiments violating Bell inequalities, and the common takeaway, the headline, was basically, local realism is dead.
Yeah, that was definitely the buzz.
But Barandes pushes back hard. He says that's a misinterpretation. First, let's be clear what local realism is. It's two ideas combined. Locality, nothing travels faster than light, no spooky action at a distance instantaneously. And realism, the idea that things, like particles, have definite properties before we measure them. They exist independently of us looking.
Right, so the particle has a spin, even if we don't know what it is yet.
Precisely. Now, Bell's theorem, according to Barandes, doesn't kill realism alone. It doesn't kill locality alone either.
It kills the combination.
It kills the combination if, and this is the crucial if, you also assume Markovianity applies to how those properties evolve or are revealed.
Ah, there it is again. The hidden assumption.
Exactly, and he makes this incredibly sharp point. Without realism, there's nothing to be local about. If properties don't exist before measurement, what is it that's supposed to be influenced locally or non-locally? Rejecting realism pulls the rug out from under the whole concept.
That actually makes a lot of sense. It feels like we're wading into philosophy here, though. Reality, existence. These aren't typical physics terms.
But Barandes argues they have to be. He says concepts like reality, existence, even consciousness are tricky, often defined circularly, but they're absolutely essential for doing science at all.
How so? Why essential?
Well, think about it. If you don't believe measurement outcomes are real in some sense, what are you even doing? Science just collapses into solipsism, the idea that only your own mind is sure to exist.
So if I believe my lab equipment is real, or that my colleague exists, or even that the number on the screen means something real,
then you're already committed to some form of realism. You have to be. Barandes puts it bluntly. If measurement outcomes don't exist in any way, science becomes incoherent.
Okay, that's a powerful counter to the idea that we should just shut up and calculate, which leads us to instrumentalism, right?
Exactly. Instrumentalism is this popular stance in quantum physics. Theories are just tools. They predict observations, and that's all that matters. Don't ask about deeper reality.
It sounds practical. If it works, don't fix it kind of thing.
It is practical as a temporary measure, but Barandes warns against accepting it as the final word, as a worldview. He thinks it's actually anti-scientific progress to just stop searching for a coherent picture of reality.
So just because the foundations are confusing right now doesn't mean we should give up and say it's just unknowable or only the math matters.
Precisely. That's mistaking a current limitation for a fundamental truth. Instrumentalism, he'd say, is a useful working method when you're stuck, but it's not a satisfactory worldview. The job is to understand, not just predict.
Which brings us back to Bell's theorem. If instrumentalism isn't the answer, and Markovianity is a questionable assumption, what did Bell actually prove? You mentioned it's often misunderstood.
Yeah, the common idea is Bell proved hidden variables are impossible. That's not quite right.
Okay, so what's the more accurate picture?
Bell showed that any hidden variable theory that is local and obeys Markovianity cannot reproduce all of quantum mechanics predictions.
And Markovianity is key again.
It's absolutely crucial. So it immediately raises questions. What if the hidden variables aren't Markovian? What if reality has some kind of memory or context dependence built in? Or what if our understanding of properties needs tweaking?
So local realism might not be dead after all. We might just need a non-Markovian version of it.
That's exactly the possibility Barandes opens up. Bell's inequalities rely on assumptions, and Markovianity is a big one that maybe, just maybe, doesn't hold at the quantum level.
Fascinating. Makes you wonder, what else are we assuming without realizing it?
A very good question. And looking forward, if we want a better theory or interpretation, Barandes suggests it needs to meet 3 key criteria.
Okay, what are they?
1, empirical adequacy. Obviously, it has to match the experiments. That's table stakes for science.
Makes sense. Number 2.
Logical coherence. It can't contradict itself. It needs to be clear, well-defined, not rely on vague notions.
Right. No fuzziness allowed. And the 3rd.
This one's critical. Emergence of macroscopic reality. The theory must explain how the everyday world we see around us, the classical world, actually arises from these quantum foundations.
And that's where something like the Copenhagen interpretation struggles, isn't it? It kind of assumes the classical world exists for measurements to happen, but doesn't explain the transition from quantum to classical.
Exactly. It puts the cart before the horse in a way. Barandes is clear. We shouldn't accept a worldview that fails to explain how the world we see emerges. It has to connect the levels.
So how do we get there? To a theory that meets these criteria?
Well, Barandes is a strong advocate for collaboration, specifically between physicists and philosophers.
Interesting. Why that combination?
Physicists bring the mathematical rigor, the experimental grounding. Philosophers, especially philosophers of physics, are trained to analyze concepts, dissect assumptions, clarify meanings, things like reality, causality, existence.
So it's not just about building bigger colliders or crunching more data.
No, he believes the next big leaps won't be purely technical. They'll be conceptual revolutions. And those require thinkers who can bridge the gap, who can handle both the hard math and the deep metaphysical questions. It needs that blend of rigor and insight.
Okay, so let's try and wrap this up. For you listening, what are the main takeaways from this dive into Barandes' ideas, it feels like? Well, first, the supposed weirdness of quantum mechanics might be an illusion.
Yeah, potentially a mathematical artifact, a result of sticking with a Markovian framework where maybe it just doesn't fit. Drop that assumption, and the weirdness might fade.
Second, realism isn't dead. In fact, it might be indispensable for science to even make sense.
Yeah.
Giving it up leads to, well, incoherence.
Right, and getting out of this current impasse likely requires that teamwork physicists and philosophers tackling the conceptual foundations together.
It suggests there's definitely space for new theories, elegant ones, hopefully, that are both empirically spot on and give us a coherent picture of what's actually going on.
The really profound thought here is that maybe, just maybe, by questioning these deep-seated assumptions like Markovianity, by asking different questions, the quantum mystery could genuinely transform into quantum clarity.
Which leaves us with a final thought for you to mull over. Where else, maybe in your own field, or just in how you understand the world generally, might there be a hidden assumption? Something taken for granted that if you questioned it could suddenly bring surprising clarity to something complex. Definitely something to think about until our next deep dive.